2023 has been a dramatic year, with many crises ongoing at the same time. We have a climate crisis with the warming of the climate, an energy crisis, and we are fighting against inflation that poses a burden to the economy. We have a war ongoing since 2022 in our neighborhood in Europe, and the war that started recently in the Middle East, both leading to humanitarian catastrophes. Also, we are still recovering from the COVID-19 pandemic. And even though that we have seen a significant decrease of the number of severe cases with COVID-19, the infection is now on the rise again. However, we are in a better situation today than in 2020, as we have vaccines that have helped us to reduce disease development and mortality. And this fast, impressive vaccine development was only possible due to scientific discoveries made many years ago on which new knowledge could be built. And the current turbulent world underlines the importance of enabling new discoveries, inventions, and improvements that will benefit humankind, and also stresses that research must be global. Scientific discoveries are driven by curiosity and deep insights to generate new knowledge. And it's impossible to determine what will be discovered in the future. Moreover, we don't know what the next challenges to humankind will be. Therefore, we need to have bottom-up and broad approaches. And the roads to discovery can be long and winding, but can lead to unanticipated surprises and openings that were not considered. And we have seen groundbreaking discoveries during the years, and we will now have the privilege and honor to listen to exemplary researchers and laureates who have increased our knowledge fundamentally and broadened our views in 3 different areas of research. The laureates of this year's Nobel Prize in Physics have given humanity new tools to explore the world of electrons inside atoms and molecules. And they managed to produce light pulses that are so short that they are measured in attoseconds. And these short pulses of light can be used to measure the rapid processes in which electrons move and change energy, previously not possible to follow. And attosecond pulses can also be used to identify different molecules, for example, in medical diagnostics. In the Nobel Prize in Chemistry, the laureates have discovered and developed quantum dots. And these nanoparticles are so small that their properties are determined by quantum phenomena. And they have many fascinating and unusual properties, such as having different colors depending on their size. And quantum dots are now being used in many applications, such as television, in LED lamps, and also to guide surgeons when they are performing surgeries, such as removing tumors. And the laureate in this year's Prize in Economic Sciences has uncovered key drivers of gender differences in the labor market. And the laureate provided the first comprehensive account of women's earnings and labor market participation, and demonstrated how and unraveled why gender differences in earnings and employment rates have changed over time, and main sources for the remaining gender gap. All these achievements not only bring new knowledge and deeper understanding, but also allow us to improve our societies in multiple ways and to take wiser decisions. And we will now listen to these prize lectures by these exceptional researchers on whose shoulders present and future humans can stand, and new giants in research will surely arise. So once again, most welcome, and my warmest congratulations to the laureates. And I now invite my colleague in the Academy of Sciences, Professor Eva Olsson, who is the chair of the Nobel Committee for Physics, to introduce the laureates in physics.
Honored Nobel Laureates, Your Excellencies, distinguished colleagues, ladies and gentlemen, a warm welcome to the Nobel Lectures in Physics. And the prize in the Nobel Prize in Physics this year is about attosecond physics. And attosecond physics is about very, very, very small timescales. So small that the number of attoseconds in 1 second is the same number as a second since our universe was born. Even though the time scale is so small, what is taking place on that small time scale is affecting our daily life because it determines properties in many different aspects. Attosecond physics reveals the life of the electrons and their dynamics. And through the knowledge of what is happening on that small time scale and with the electrons, we get the ability and the knowledge to make new tailored materials. We also can design electronics using new concepts, and we can develop methods for medicine of most importance for mankind. And our laureates, they discovered that it was possible to generate these very short light pulses. They developed methods to measure the duration of the light pulses, and they also developed methods for generating pulse trains and also individual isolated light pulses of the attosecond duration. And our Nobel laureates in physics, we will see here, and I get some help to switch to the next slide. And while we're figuring out how to go there. So, here they are, yes. So, our Nobel laureates in physics this year is Pierre Agostini, Ferenc Krausz, and Anne Lollier. And it is my pleasure now to introduce our first speaker, and this is Anne Lollier. So please join me in welcoming Anne.
So good morning. It's a pleasure to be here, and let me start by thanking the Royal Swedish Academy of Sciences and the Nobel Foundation for this prize and for the pleasure, the privilege to give this Nobel lecture. So I will tell you about how we arrived to these attosecond pulses. This is a history of attosecond science with the first years, progress in technology and in understanding, measurement of attosecond pulses, and then opening to research fields and applications. And I will go through the first two parts and leave part 3 to my co-laureates, measurement of attosecond pulses. I will, in the end, just say a few words about some applications. Nothing would have happened without the invention of the laser in 1960 by Theodor Meinmann. And the Nobel Prize in Physics was given to the background for laser in 1964 to Townes, Bazoff, and Prokhorov. And you have here a picture of one of the first lasers, a ruby laser. Now, what we are going to use in our research the properties of the laser are first the possibility to generate short laser pulses, and especially the possibility to, by focusing these pulses, to achieve a very high intensity. So the invention of the laser led to new research fields, and the first one is nonlinear optics. This is a picture of an experiment performed by Peter Franken in 1961, immediately after the invention of the laser. And you see a ruby laser, which is focused by a lens into a material, and our experiment will look very much the same. And then the radiation is analyzed by a prism and detected by a detector. In this process, an atom absorbs 2 photons. It's a nonlinear optical process, and emit a photon at frequency 2 omega. This is second harmonic generation, the first nonlinear optical processes that was discovered. Now, another research field that started after the invention of the laser is atoms in strong fields or multiphoton processes that were predicted already in 1934 by Maria Goeppert-Mayer. And in the multiphoton processes, an atom absorbs several photons simultaneously. It can be excited, it can be ionized. In 1979, Pierre Agostini discovered the process of above-threshold ionization, where an atom is ionized by absorbing more photon that is necessary for ionization. And this is detected by observing electrons, and one observes several peaks. Now, an atom can also be multiply ionized, and this was actually my thesis work at the beginning of the 80s. Now, at that time, the question arose, is it possible to produce excited atoms or excited ions that then would decay by emitting fluorescence light? So we set up an experiment. This was in France, at the Commissariat à l'énergie atomique. We set up an experiment to observe this fluorescence light. Fluorescence light is emitted in all directions. So we had actually 2 axes of detection, one along the direction of the propagation axis of the laser with a grating and a detector, and one perpendicular to it. And this is the laser that was used at that time, an iridium YAG laser, 1 micrometer wavelength, and pulse duration was 40 picosecond. You have an oscillator here and 2 amplifiers. And this is a picture of the experiment setup. You have a laser is coming from the right. You have a lens focusing the laser into a chamber, and the radiation is detected along the propagation axis with a grating and a detector, and perpendicular to it. The intensity reached in the medium, so here we have also a pulsed gas jet delivering some gas of atoms. So the intensity in the medium reached several times 10 to the 13 watts per square centimeter, which is quite high. What did we see? Well, we never saw anything perpendicular to the detection axis, so I'm not going to discuss that anymore. And we didn't see much fluorescence. What we saw was very high order harmonics of the laser field. And this is one of the first spectra obtained in argon gas. And what you see here are harmonics 13, 15, up to 31st harmonic of the laser field. So when it says 13 here, that means that the frequency is equal to 13 times the laser frequency. Now, if we plot the intensity distribution of these high harmonics, we get typical behavior with the decrease, a plateau behavior where all the harmonics have the same intensity, and this is ending with a cutoff. And this was very unexpected. First, it was not expected to see so many high-order harmonics. Then, it was not expected to have this plateau behavior. One thought that it would be more and more difficult to generate high-order harmonics. This was based on some kind of perturbation theory thinking at the time, that based on an expansion of the polarization induced in the medium in powers of the electric field, for this expansion to be valid, one has to assume that the first order is much larger than the third and much larger than the fifth. And this was not the case. You can notice that I'm only talking about odd orders of the laser, and this is due to a symmetry property of the medium. It has the inversion symmetry, so the even order harmonics are actually killed. Now, if you go from a frequency of the laser light, which is in the infrared region, and you multiply this frequency by, let's say, 33, you end up in the extreme ultraviolet region of the spectrum. So it's below X-rays, but above ultraviolet light. So this light is invisible, and it does not propagate in air, so we have to evacuate. Now, let's make a little bit analogy with music here. When we think about harmonics, usually think about music. What we do is actually very similar to what happens when the bow of a violin hits a string of the violin. It produces not only a single tone, but also overtones. And this is what actually makes the clang, the timbre of a music instrument, is how many of these overtones we have. In our experiment, we produce not harmonics of sound, but harmonics of light. And the violin is the gas of atoms, and the bow of the violin is the laser pulse. Now, this process requires it at the border of two fields, atomic physics and nonlinear optics. Atomic physics is the description of the response of an atom to the laser field. And this is, we are in the quantum world. This is described by a Schrödinger equation that you have here, where you have here the atomic potential and the laser-atom interaction. In this problem, we can describe the laser field classically, and we use the dipole approximation. Now, the second aspect is nonlinear optics, the response of many atoms to the radiation. It's not enough that each atoms generate these high harmonics. You also need to have efficient harmonic generation to have the emission from all of the atoms in the medium in phase, act coherently. And this is described by Maxwell equations of electromagnetism, which can simplify to a wave equation as what is written here. E here is the generated field in the medium, and P is the polarization in the medium induced by the laser field. So the first attempt, let me say one more thing, again, analogy to music. This many atom response, you can think of a gigantic orchestra. All of the musicians in this orchestra need to play with the same pace. And the number of atoms in this orchestra is trillions of atoms, many more than the number of people on Earth, just to give you a little bit an order of magnitude. Now, the first attempt to describe these processes was to simply solve these two equations which I just wrote. And these are calculations of this single atom response, solving numerically the Schrödinger equation. And you see that the agreement between theory and experiment is quite good. in itself, it's a bit surprising because at that time we thought that many atom response would be very different for the different harmonic order. It would be more and more difficult to phase match the process. So it was really necessary to also solve the second equation, the wave equation. And this is what was done here. You see that we obtain a rather good agreement, again, with the experimental behavior, and we can reproduce this plateau and cutoff behavior. So we can simulate the experiment, but we don't really understand the physics behind. Approximately at the same time was asked the question, could it be that these high-order harmonics form in the time domain a series, a train of attosecond pulses? And the idea is the following. Consider, let's say, 3 harmonics, 17, 19, and 21, and assume that these harmonics are all in phase at a certain time. They are phase-locked. If they are in phase, synchronized, at a certain time, they will be again in phase after half the laser cycle. So now if you sum these 3 waves, you see that we get constructive interference when they are in phase and destructive interference where they are not in phase. We can confine the light into short pulses. And if we plot the intensity corresponding to this electric field, you get a train of attosecond pulses. If you sum not only 3 harmonics, but let's say 10 harmonics, and you assume they are phase-locked, you obtain a train of very short light pulse. Why is it interesting? Because the evolution of the pulse duration of lasers had come to a stop. This is the evolution of the pulse duration of dye lasers decreasing from picoseconds down to a few femtoseconds, and a couple of years later, titanium sapphire laser would also arrive at the stop of about 2 femtoseconds. And the reason for this stop is that we are talking about light pulses. And to talk about a light pulse, you need to have at least 1 optical period in this pulse. And the optical period of, for example, a titanium sapphire laser is 2.6 femtoseconds. So in order to decrease the pulse duration, you need to decrease the optical period, which means to go to higher frequencies. Now, the second condition to get short pulses is that you need a broad bandwidth. This is just an expression of Heisenberg principle. To get a short time, you need a broad bandwidth. And this high-order harmonics provided both higher frequencies in the extreme ultraviolet and the broad bandwidth, this plateau behavior. So this was a very exciting question. So now I'm coming to the second part of this talk, which is progress in understanding and progress in technology. And I would like to start by progress in technology. At the beginning of the 90s, there was a huge progress in laser technology. First with the chirp pulse amplification, which led to a Nobel Prize to Gérard Mourou and Donna Strickland in 2018. There was the discovery of a new material, titanium sapphire, by Peter Moulton, and then a new way to generate short pulses in the laser oscillator, which was Kerr-Lenz mode locking. And here you have 3 Swedish scientists, Sune Svanberg, Anders Persson, Claes-Göran Wahlström, that look at this new laser technology, and they decide to really invest into this new laser technology. This was very risky because it was not clear that it would work, but they really invest into this technology and build the high-power laser facility in Lund with terawatt titanium sapphire laser. This was really the perfect laser to study high order harmonic generation with a short duration of the order of 100 femtosecond, and at that time a high repetition rate, 10 laser shots per second, 10 hertz. In parallel to that, there was also a progress in instrumentation. In Saclay, we built a dedicated instrument to study high-order harmonic generation, which you see here. And these instruments include gas jet, optics to analyze the radiation, and a detector. And here you have myself, much younger, but together with Philippe Balcou and Pascal Salière, my first PhD students, we are here in the audience today. And this is also the time where personal computers came into the laboratory. The first experiment that I mentioned, we were using a printer to record the signal. Now, personal computers started to really come into the lab, and we could, thanks to these computers, really take data in a very completely different way. So we performed, so this led to very nice experiments combining this dedicated instrumentation and this new laser system, titanium sapphire. And I show here one of the first spectrum obtained in neon using this laser by a group in Stanford. And you see a beautiful harmonic spectrum with a very large plateau here. This decrease at the beginning is simply due to the decrease in efficiency of the grating. And you have the cutoff in this region. So you see that we go to the 111th harmonic. And in Lund, together with collaboration Lund and Saclay, we could not only take harmonic spectra, but really study these harmonics as a function of different parameters. For example, here as a function of the laser intensity. Now, approximately at the same time came really a breakthrough in the theoretical understanding of this process with the three-step model. So I would like to say here that this prize is given to the experimental method in attosecond science, but the theorists have played a very, very big role in attosecond science, and in particular in the understanding and this three-step model. And this was shown approximately at the same time by Ken Kullander and Ken Schaefer, by Paul Corkum in Canada, and Maciek Lewenstein and co-workers here, Misha Ivanov, presented a quantum formulation of this three-step model called the strong field approximation, which was going to have a very strong impact in the field. So this three-step model is presented here. What happens is that you have an atom in a strong laser field, and this laser field is really strong. It distorts the atomic potential. It's bend this potential, and here you have a barrier. So an electron in the ground state, this is quantum mechanics, there is a certain probability for the electrons to tunnel through this barrier. Then the electron is driven away by the laser field. The laser field changes sign, the electron is pushed back towards the atom, and then there is a certain probability of recombination. In this excursion, the electron has gained some kinetic energy, and the excess energy is emitted in the form of a high-energy photon. And this process is repeated every half laser cycle on one side and the other side, and again, leading to emission of light every half cycle of the laser. Now, what about attosecond pulses? I just remind you that we have discussed that if we had phase-locked harmonics in the time domain, we would have 1 pulse per half cycle. So what was this new theoretical understanding telling us? And here is the bad surprise. This was the result of the calculation. Light everywhere, no 1 pulse per cycle, so no phase-locked harmonics. So the attosecond idea at that time was quite controversial and not so clear. How can we understand this multiple pulse emission? Actually, we can understand very simply using this 3-step model and looking at the possible electron trajectory. This is just a very simple picture of these trajectories, electron going out and coming back. I put in colors the energy that the electron have when they return. So you have higher and higher energy, depending on when the electron is born. But there are also trajectories which takes longer time and leads to a similar type of energy. So when you look at the possible trajectory, you find that there are short trajectory and long trajectory leading to the same kinetic energy. And this complex picture leads to this complex result in the time domain. Now, we could actually verify the existence of these trajectories in the laboratory. This is an experiment performed in Lund in '98, and you have some of the participants here, Mette Gårde, who is in the audience, Ted Hensch, Marco Bellini, and others. And what we did in this experiment was to look at the coherence of this high harmonic. Is it coherence light? And to do that, we duplicate the harmonic sources, and we look at whether this light interferes in the far field. If this is coherent, we should have interferences. And indeed, you see here on the 15th harmonic that there are beautiful interference fringes. What you can also see in this picture is that there are now 2 contributions. There is collimated radiation and more divergent contribution, which we could identify to the contribution from the short trajectory and from the long trajectory. Now, we could also delay one of the source relative to the other and look at what happens to the interference fringes. And you see that in this case, the interference are still present for the collimated radiation, while they are gone for the more divergent contribution, which shows different properties of these 2 contributions, short and long trajectory. What happens to the other side? Strong field nonlinear optics, the response of many atoms, was also a progress in this part as well. So to achieve fast matching here, we need the phase of the pulse which is generated to be equal to the phase of the polarization induced in the medium. So we need these 2 wave vectors here to be equal. And this difference in wave vector depends on the dispersion in the partially ionized medium, depends on the laser focusing, but it also depends, and that's the important thing, on the electron trajectory, whether it's short or long. And this gave us the idea, or maybe in some condition, only one of these trajectory can survive, only one of these trajectory get phase match. And indeed, this is what we got. This is, in dashed line, you have the single atom response, while in blue, you have the temporal structure of the total attosecond pulse train. So we recover 1 attosecond pulse per laser half cycle and phase-locked harmonics. So at this point, we think that, or maybe we have attosecond pulses, but what is very important is to measure attosecond pulses. Before I come to the conclusion of this talk, let me point out that at the end of the 90s, there is a lot of progress, both in laser and in high-order harmonic technology. And let me just flash some of this progress. First, now we can generate laser pulses that are very short, few cycles, and then the importance of the carrier envelope phase is pointed out. And the carrier envelope phase is the phase offset between the electric field and the envelope. And this was going to be very important for the generation of single attosecond pulses. Then you have novel medium geometries like cell or capillaries. You have also new media that are being explored, molecules. You have a push toward higher photon energy using short laser pulse and especially long wavelength lasers. And you have also a push toward higher pulse energy in the microjoule range using clever focusing geometries. So now I am going to jump over this part 3, and I would like to finish this presentation by just giving you 2 examples of application. Very different example. One is very fundamental. This is about electron dynamics, and one is much more applied. So electron dynamics. I think that's the exciting thing about attosecond pulse is we can now follow the dynamics of electrons in matter. And here I take one example, which is very simple. It's photoionization, a process that was understood theoretically by Albert Einstein in 1905. And he actually got the Nobel Prize just for the discovery of the law of the photoelectric effect. So what we can do, and I'm going to talk about photoionization of atoms. What we can do, thanks to attosecond pulse, is we can now answer a question: how long time it takes for an electron to propagate in the continuum? What are the wave quantum properties of the photoelectron? And I'm not going to explain how we do these measurements. I just want to try to make you understand what we can do, again, by using an analogy with music. In music, you keep the pace by the conductor is keeping the pace, or a metronome can be used to keep the pace, and the metronome has a motion like this. So this is a wave motion, both the conductor and the metronome, which is due to the mechanical motion of the tip of the metronome. And this is exactly what we do. We are looking at oscillations, such as this one here, and we are going to compare the position of the maxima of this oscillation and this oscillation. Here I'm talking about photoionization of neon atoms in the 2s shell, which I'm comparing to photoionization of neon in the 2p shell. And what do we measure? It's always interesting to talk about time by showing a clock. In our measurements, 1 hour on a clock is 1/2 period of the laser, which is 1.3 femtosecond. So 1 hour is here 1,300 attosecond. And what we can measure very accurately is the position of 2 arrows on this clock, which correspond to the time it takes for the electron to ionize from the 2s shell and from the 2p shell. We don't know where these 2 clocks are on this clock, but we can measure the difference in time between these arrows. And now I'm showing some results showing that indeed we can measure this relative time quite accurately within tenths of attosecond. The second application I would like to mention is really going into a completely different direction now, very applied, and this is now belonging not to the research laboratories anymore, but to industry. And this is an application not so much about the temporal structure of these high-order harmonics, not so much about attosecond pulse, but about simply an application of this radiation, which is in the extreme ultraviolet range, and which is very broad in frequency. So now harmonic generation are being used to control wafers, silicon wafers, which contain integrated circuits, and this technique is used for the next generation instruments that will control this integrated circuit with very, very small dimensions of the order of 10 nanometer or below. And this control is made not only in 2D, but in 3D. And what is really used here is the fact that we have so many frequencies. And this is developed by an industry, ASML in Holland. Now, to conclude, I would like to thank many people, all of my colleagues during all of these years. And I'm showing here some group pictures, not since 1987, just the last 15 years or so. I would like to also thank the organizations that have funded this research, the Swedish Science Council, Swedish Research Council, and the European Research Council, the Wallenberg Foundation. And last but not least, I would like to thank my family, Klaus-Göran, Oscar, and Victor. Thank you for your attention.
So we're just going to fix the rug here to make sure that we don't trip on it. Thank you very much, Anne, for this historical exposé. And now we come to the next step. And this is now Pierre Agostini. And Pierre Agostini is from the Ohio State University. So please welcome. Please join me in welcoming Professor Agostini.
Thank you. Yeah. Good morning, everyone. And okay, the title of my talk is The Genesis of an Attosecond pulse trade. It has nothing to do with trades, but we'll see. Okay, if some of you have never heard the word attosecond before, it's a very short time. It's billions of a second. And so one natural question that could arise is this series of, from second to nanoseconds and femtoseconds and attoseconds and more is infinite. Is it possible that to divide the time indefinitely like that? From a physics point of view, I would say that that's doubtful, because first of all, it takes more and more energy to produce those short pulses, and at the end, we'll hit the Planck time, and that's an absolute limit. We are still very far from that time, but it's probable that, okay, the series is not infinite, and you cannot divide the time indefinitely. So, in this lecture, I would like to tell you about the physics of rabbit, and then I will tell you about an application of those attosecond pulse trades, and especially time application on double ionization. Okay, it's quite obvious that if you need to make an attosecond, then you need two things. First of all, you need a very short period for the light. And this means high frequency, and this means that you have to go into a domain which is soft X-ray and XUV or soft X-rays. Then what you need is a coherent bandwidth which is large enough to support the attosecond pulses. And this is a condition that must be fulfilled. So the harmonics that Anne L'Huillier talked about before is, or seems to be, a perfect candidate to produce those pulses. First of all, the frequency is high, and it can be up to 100 times the infrared frequency of the lasers. And then the bandwidth is quickly very wide, and so all the qualities are supposed to be here. So, indeed, back in 1992, those two guys, my old friend Kyozo Farkas, and his co-worker Chabad Todd, calculated that if those harmonics are in phase, if they are phase locked, it's say, and then in the time domain that would correspond to a sequence of periodic pulses of very short duration. Unfortunately, at that time, this calculation by Anne L'Huillier and co-worker seems to show that the phases were not at all as hoped, but there was looking like random, absolutely random, and so except perhaps in the cutoff region where there are no photons at all. So, yeah, I come back to this question a bit later. Okay, then I have to introduce you to the above threshold ionization process. And for that, I will start with Einstein photo effect that was mentioned already. So Einstein has the idea that light is made of photons, and not of a field, but of photons. And the photons have a specific and definite energy of h nu, the product of the Planck constant by the frequency. So an electron can absorb or emit photons, okay, integer energy of photons. And now if the photon energy is large enough, then you can liberate, you can free one electron from the potential well in which it is. Okay, so this is well known from all the students and the high school students, I guess. The kinetic energy of the electron which is freed is the difference between the photon energy h nu and the potential energy the electron is kept by in the atom or in the solid or anything. All right, then that was the time of Einstein, 1905. But in the 60s, in 61, the laser was invented by Mayman, and actually it was possible to ionize an atom with photons which were smaller than IP. And then you just had to pile up a number of photons. For instance, here, the kinetic energy is equal to 3h nu minus IP on this graphic. So the study of this MPI, so-called MPI, multiphoton ionization, started in Russia at the Lebedev Institute, and there are a number of papers from the mid-60s about that. Okay, and then I come to the above threshold ionization, or ATI, and it was, you know, by measuring the kinetic energy of the photoelectrons, it was immediately seen that electrons are more energy than predicted by the Einstein photo effect, and by the energy of the electrons could be that energy minimum 3 h nu minus IP, for instance, in this case, plus another photon or two other photons. So you could see that as peaks in the photoelectron spectra. So, how to measure the phase? The phase of the harmonics is the thing that is the key to attosecond pulses. And so, how to measure those phases? First of all, you need a nonlinear optics process. I'm not proving that here, but I ask you to take my word for it. The problem was that harmonics were not strong enough to do those multiphoton or nonlinear optics processes. So the solution was to mix the harmonics with a strong laser, and this could result easily in two-photon ATI or two-photon ionization. So we have now this case of two-color, two-photon transition. One is with a harmonic or with a photon which is large enough, and then we have ATI, that is the atom absorbs one photon more, but one photon from the strong laser. So we could have also more complicated things like that, where we have three colors to start from, the two consecutive order harmonics, and one photon being absorbed and one photon being emitted. All right, that's the key of the measurements we have done. And in 1996, those three theorists from Paris, Vignard, Tayeb, and Mackay, calculated that if you have an atom which is ionized by two colors to start from, right? Two consecutive order harmonics, then you should have two peaks, one for each of these colors. And if you mix those two colors with a laser, then the atom can absorb two photons yeah, one photon from harmonics and one laser photon, or absorb one bigger photon from the harmonics and emits one photon. And since we know that those harmonics are only odd order harmonics, they are separated by twice the laser frequency, twice the frequency omega. And if one absorbs one photon from the laser and the other emits one photon from the laser, you added up to the same energy. This energy, gives rise, of course, to an interference. And okay, I'm sorry for the equation, but the result of this interference is that the amplitude of the middle peak, which is called the sideband, is given by this simple mathematical formula. And in this formula, the frequency is the frequency at which this sidebands oscillate, and the phase difference, which is the thing that we are looking at, looking for, is this factor here, delta phi q. So it's enough to change the delay and measure the amplitude of the sidebands to determine what the delta phi q is, and to determine the phase of the harmonics or the phase difference of the harmonics, and to check if whether or not we have attosecond pulses. On top of this delta phi q, there is a small correction that had to be calculated at that time, and I'll come back to that in a second. Okay, how do we implement the theory in an experiment? Okay, this is, I'm not going into all the details here, but the important thing was a mask, which was dividing the beam, the initial beam, into two parts. Then we had a couple of glass windows which could be oriented and which introduced between the two beams an attosecond delay, a delay with attosecond precision. Then there is, of course, the jet where the harmonics are created. And then there is something which I called here a pinhole, which is just a hole in a piece of metal. And this has a very important role, as we will see immediately. Okay, this is the first measurement of the harmonic phases in our experiment 20 years ago. And so what you see here is the spectrum on the top box, a spectrum with no infrared, without these laser photons. And so what you see are the peaks corresponding to the harmonics. Okay, then we introduce the laser, we superpose the laser to this harmonics beam, and we have more peaks in the spectrum, and those are the sidebands in between each of the initial peaks. And the amplitude of the sidebands changes with the delay, all right? So the mathematical formula of Vignard-Tayeb-Mackay, and from these oscillations, one can derive the phase of the harmonics, the phase that would decide whether or not we have attosecond. So it turns out that from these phases, the phases are very well behaved. Not at all the random things that was predicted by Antoine and Maciek, but from the amplitude measurements and from the phases measurement, then one can reconstruct the time domain of the pulses of the light, and we had this train. I mean, train meaning here a sequence of periodic pulses, and the pulse duration was at that time something like 200 attoseconds. That's much longer than, okay, that was 20 years ago, right? Now, probably Ferenc will talk about that, but the pulses have shrinked to 43 attoseconds, right? I think that's the last number I thought. Okay, the question is, does this, that's the calculation of Anne that we saw a moment ago, contradict that? I mean, this behavior which look completely random, and this one looks pretty nice. So is there a contradiction between the two? Okay, I'm not going to talk about the details which have been already described by Anne, but the question is this angular distribution of the two amplitude that interfere and that make the phases look absolutely random, that can be really solved with a very small and cheap things, which is probably the cheapest thing in our experimental setup. And so this is a pinhole that isolates one of the two amplitudes that creates the problem with the randomness of the phases. So this is done by just because of the angular distribution is different, and if we put somewhere in the beam this very simple gadget of a pinhole, then this suppresses completely one of the interference amplitude, and from there, if the interference is suppressed, then the behavior of the phase is fine. One word about the small correction. You remember perhaps there are two terms, the harmonic phase difference, and there was this small correction. The small correction has made a terrific career in the past 10 years or so, under the name of photoionization delay. That's the technique that was used to measure the time delay between, the time delay taken for the electrons to be removed in the photoionization process. Well, I put some titles there, but you can see in the last one that, okay, in one title there is already zeptosecond coming, so the future is coming here. Okay, now I guess I have a few pictures that have been provided by Philippe Balcou of the laser we used at that time. That's not much of a picture, but at least I've been guaranteed that it's authentic. Okay, those are the two windows that were used in the experiment and in the setup that we used to control the delay between the two beams. So it's, yeah, the two windows, this is a window clearly on the left. On the right, there is a small part of a window, the small central part is the window, which has exactly the same thickness as the other one, because it has been taken from the other one. And so, yeah, this is again a courtesy of Philippe Balcou and Amel Zahir and CNRS and Celia. So this is not really the usual, the authentic one, the old one, which have disappeared, but it is a replica which is exactly the same and which has been actually used in an experiment. I'd like to show some picture of our students at the time. I mean, Elena, Thomas, and Pierre-Marie Paul, which were, I think, in the audience somewhere. Philippe Balcou is here. This has provided a number of things. And one special mention is about Müller, Professor Müller, who not only invented this setup that we have used in the experiment, but also invented this wonderful acronym of RABBIT, whose explanation is in the title of this paper, which came out 1 year after the first one, and is a reconstruction of attosecond harmonic beat by interference of two-photon transition. Okay, then you know everything. Okay, then I would like to talk a little bit about an application. And the subject of this second part is the strong field double ionization. Okay, first I could show you, okay, that's show and tell. A modern atom beam line at Ohio State. You see tubing and, the electron spectrometer is down there. The laser is somewhere in another room. And so the laser beam is coming through those tubes. It's under vacuum. Everything is under vacuum because all those harmonics are XUV or XUV or soft X-rays. So naturally now everything is automatic. In the first experiment we were turning the glasses by hand to start from, so yeah, all the time. Now it's completely automatic, and what you see here is a sequence of measurements, and first of all the laser are kilohertz repetition rate, so it's much more accurate and precise now. Okay, so double ionization. I mean, once you have extracted one electron for an atom, so you have an ion, and if you try to extract a second electron, then the work you have to apply to the atom is about twice the first one. So it's predicted from that would be much more difficult to extract the second electron than to extract the first one. But okay, an experiment or several experiments in the 1924 showed that this was not at all the case, and that ionization of a double ionization was not that difficult. So one of the explanations was provided by those guys, Paul Korkum, Ken Kullander, and Ken Schaefer. Ken Schaefer is here somewhere. And the idea is that if you extract one electron in the presence of a strong field, this electron can be accelerated by the field, and then stand back to the nucleus where it started from, and extract another electron by a E2E process, by sort of billiard balls, right? So the probability of this element is much larger than what expected by, say, multiphoton processes, perturbative multiphoton processes. Okay, now the experiment that has been done in Columbus at Ohio State by those students and under the direction of Lou DiMauro is the following. Okay, first we have this strain of attosecond pulses that we can, absolutely precisely delay with respect to the optical cycle of the laser. So we can decide exactly at what moment, at what time within the attosecond pulse duration the electron will be ejected. And then we can detect or observe the return time of these electrons, the time that separates the emission from its return to the nucleus, by observing the doubly charged ions. And from the knowledge of the departure time and the return time, we can reconstruct the electron motion exactly. So that's one example of how you can use those attosecond pulses to control and observe electrons' motion in a strong field. Just yeah, a quick look towards the future. So far, all attosecond pulses are created by laser, visible or infrared laser, and harmonics. Now, the problem with the harmonics is that they are not very powerful. I mean, they are sort of weak, and to observe nonlinear processes with them, we have to mix them with a strong laser. Now, at a LINAC coherent light source, X-ray free electron lasers, which is this this small setup of 1 kilometer long or something. I'm finished. People have already found that they are able to create isolated attosecond pulses with gigawatt peak power. So that's at least a factor 10 above the current harmonics at the moment. So maybe the future of the attosecond is not in the lab and not with our laser and harmonics, but with this LCLS X-ray free electron laser. Okay. Thank you.
So, now we have heard about how to measure the duration of these short light pulses, and also how to create the pulse trains, and also about applications in fundamental science. Now we come to the creation of individual short light pulses, and we are going to welcome Professor and Director Ferenc Krausz. So please join me in welcoming him.
Thank you. Let's see. Good morning, ladies and gentlemen. It is a tremendous honor to be here, and I thank the Royal Swedish Academy for bestowing it on me. It's still hard to believe. I would also like to thank all persons in my life who supported me, helped me learn, grow, and achieve: my family, my teachers in Hungary, my co-workers in Austria and in Germany, and our collaborators from all over the world. Some of them will show up on my slides, and I already now cordially thank them, as well as the many more who are not going to show up, for their invaluable contributions, without which I would certainly not stand here today. These two gentlemen played a very special role. I owe them very, very special thanks and gratitude. Arnold Schmidt's guidance and Paul Corkum's deep insight into electron phenomena have profoundly and decisively influenced my path. This lecture is going to be devoted to how attosecond physics opens the door to the world of subatomic motions of electrons, which were inaccessible to human observation until the turn of the new millennium. For decades after following its discovery, this elementary particle was thought, when bound in atoms, to be revolving around the nucleus. Eventually, quantum mechanics revealed that subatomic motion can only emerge by exciting an electron from its ground quantum state to a superposition of stationary states, and the resultant temporal variation of the electron's probability density constitutes the closest analogy to classical motion, exemplified here by the dipole oscillations in the 1s2p superposition state in hydrogen. One of the messages that I would like you to take home from my lecture is that control is absolutely central to time-resolved observation and exploration. For example, the control of electrons' current by transistors in macroscopic nanoscale but yet macroscopic circuits with microwave electric fields underlies the capturing of fast-varying electronic signals in macroscopic circuits. Analogously, the control of electrons' current by the electric field of light opens the door to observing and eventually even controlling electron phenomena in atomic and even subatomic dimensions. But how actually to control the electric field of light in order to be able to control with this controlled force that it exerts on these electrically charged particles to control the atomic scale electron current? 4 Nobel Prize winning concepts paved the way. Lasers utilizing nonlinear optics and chirp pulse amplification can yield ultra-short, very powerful ultra-short pulses. Whereas the control of the laser frequency comb can lead to pulses with a controlled waveform. Controlling the waveform of light actually means that we have to shape, we shape the electric field within its oscillation period. What does this mean? Well, what it technically requires is an octave spanning bandwidth. Lacking lasers with such a gain bandwidth, we have no other choice but try to broaden the spectrum of the pulses outside the laser. And that's exactly what we can do in a wonderful device invented in Milano by Orazio Suelto, Santo De Silvestri, Mauro Nisoli. We can send a short laser pulse through a gas filled hollow fiber where it suffers, it is subjected to cell phase modulation, and this nonlinear process broadens its frequency spectrum. The result is a pulse that carries a frequency sweep with a strongly broadened spectrum, and these pulses can subsequently be compressed by another wonderful device, chirped multi-layer mirrors invented in Budapest by Robert Sipperch and Karpat Ferenc. And these two devices together are able to actually advance femtosecond technology to its limits, to the limit that is imposed by nature to the limit of a single wave cycle. So thanks to these two technical developments, powerful pulses consisting of a single intense oscillation cycle became available with controlled carrier envelope phase since 2003, and with this latter development they actually opened the door to precision attosecond metrology. But before I come to that, I just would step back a couple of years to briefly review the first attosecond generation and measurement experiment in Vienna. The multi-cycle driving laser pulses used in the experiments of Anne and Pierre were replaced by pulses comprising a single wave cycle, single very intense wave cycle. When focused on atoms, the extremely rapid turn-on in these pulses implies an unprecedented rate and temporal confinement of ionization, and as a direct consequence, a very short, very brief emission of XUV light from the higher order harmonic generation process, particularly if we filter the highest order harmonics, in our case, with a bandpass multilayer, which also focuses the beam to a second jet of neon gas, where the XUV pulse knocks electrons free in the presence of the few cycle laser field, and actually provided the first, first very strong experimental indication of the existence of an isolated sub-femtosecond pulse in a series of experiments performed by Michael Henschel and Reinhard Kimberger in our laboratory at that time at the Technical University of Vienna back in 2001. A couple of years later, laser pulses with controlled waveform enabled precision attosecond metrology by implementing an ingenious concept of Paul Corkum, the concept of a light field-driven streak camera. The XUV pulse again hits neon atoms, again in the presence of the laser field, but this time we measure the time of flight of those electrons which are catapulted from the atoms parallel to the direction of the laser field. Depending on their moment of release, the laser field accelerates or decelerates them. And you see here from this equation that now physics further simplified after the electron is liberated. The laser field is so strong that actually we can describe the motion in a very good approximation classically. Just Newton's equation is being solved here to calculate this delta P, which is the kick in the back of the electron to move it faster or slower. And this very kick is depending on the moment of release, and this actually maps the temporal profile of the XUV pulse to a final momentum distribution of photoelectrons. Recording this XUV-induced laser field streaked photoelectron spectra as a function of delay results in a spectrogram which allows an ambiguous complete retrieval of both the laser waveform as well as the complex amplitude of the attosecond XUV pulse. So this experiment actually demonstrates how control enables observation, this time on an attosecond time scale. and actually renders the basic tools, the attosecond varying force that this light electric field exerts on electrons, and the attosecond duration XUV emission available for real-time observation and control of electron light phenomena. With these tools in place, we can set out to perform attosecond time-resolved spectroscopy. You have learned from the wonderful talk of Anne how actually such spectroscopy can be done by using XUV pulses to kind of trigger the motion, like ionization, and use the basically laser field to capture the motion, right? Here I turn the game around, and I will show you an example where we use actually the attosecond varying and attosecond controlled force that our single cycle laser pulse exerts on electrons to trigger the motion, and use the attosecond XUV pulse to actually capture it, to take the snapshots with a delay and try to reconstruct the motion from this series of snapshots. So basically, we just use this single cycle laser field to ionize an atom, actually in the same focus which we used before to characterize the tools by attosecond streaking. And this time we put some other gas there, krypton gas, and the single cycle laser field actually ionizes this gas. And we send the XUV pulse with some delay through the ionizing medium and analyze its spectrum. It's the energy distribution of the photons contained in this attosecond XUV probe. And when the system starts ionizing, then we see some changes in the spectrum, and that's what, with the help of some theory, as we will see in a moment, gives us information about how the electron is actually liberated and is coming out, is catapulted out of the atom. So obviously, this kind of measurement is able to provide direct time domain insight into what I think can be considered arguably the most fundamental strong field phenomenon, optical field-induced electron tunneling. Here we can observe how this process, in this case in krypton atoms, is substantially confined to the central wave cycle of a cosine-shaped near-infrared waveform, which we have measured simultaneously by attosecond streaking. So remember, two attosecond techniques are being employed in this very experiment: attosecond transient absorption spectroscopy, which leads to the transient absorption spectra I'm going to show you in a moment, and simultaneously attosecond streaking to learn precisely at which moment actually, or what is the reference in the time, on the time scale, where is the time zero with respect to which we delay our attosecond XUV pulse. One of the exciting discoveries that we learned from this experiment was that the about 700 attosecond rise time of the ion population turned out to be significantly slower than predicted by the quasi-static A-decay theory. So this kind of non-adiabatic tunneling that could not have been discovered by any previous spectroscopy. When subjecting these krypton atoms to this strong field, actually the electrons can be liberated from two different so-called spin orbit quantum states of the 4p subshell of krypton with comparable probability. This means that the hole in the electron cloud of this krypton atom is created in a superposition state, because the hole can be either in one or in the other spin orbit state. Remember, we learned at the beginning of this lecture that putting the electron, or in this case the hole, same thing, in a superposition state means motion. subatomic motion. And indeed, the sequence of transient absorption spectra that is shown here in a false color representation does exhibit pronounced temporal variation, periodic temporal variation for increasing delay of the XUV probe. The 6 femtosecond delay period actually precisely corresponds to the 0.7 electron volt energy separation between the two spin orbit levels. To develop the film from these transient absorption spectra captured with 150 attosecond exposure, the photographer's job here is taken over by theorists, and I would very much like to join previous speakers, Anne and Pierre, to emphasize how incredibly important the role of theorists was in the emergence of attosecond science. So here you see the result of that modeling, and the excellent agreement between theory and experiment allows actually to reconstruct the attosecond snapshots of the whole density distribution versus time delay, and even the initial quantum phase between the two components of the wave packet of this whole that we create. So from all this information, we can completely reconstruct the subatomic motion following tunneling ionization. Here in a slow motion replay with a temporal magnification of 10 to the 15. When rendering these motions accessible to human observation, attosecond spectroscopy furnishes us with a temporal magnifying power that is equivalent to the combined magnifying power of a space telescope and an electron microscope. In the words of Eva Olsson, we can now open the door to the world of electrons. Attosecond physics gives us the opportunity to understand mechanisms that are governed by electrons. The next step will be utilizing them. But which applications are likely to yield, in the words of Max Planck, the richest and most lasting gains that we can possibly draw from this new perception? If you accept that this may be a right question, we have already mastered what Ernie Rubik considers to be the most important and difficult task, namely finding the right question. My tentative answers appear to be deep dives into the delicate details of light-electron energy exchange at the nanoscale and into the molecular composition of functional constituents, biofluids, body fluids, and tissues of living organisms for tackling contemporary grand challenges. Ever since the beginning of the new millennium, advancement of processor performance was driven by miniaturization, whilst the clock rate actually determining the speed of processing was stagnating at about 10 gigahertz. Can attosecond physics possibly contribute to exploiting the fourth dimension for further advancing electron-based signal processing? Another contemporary grand question relates to the millionth of premature deaths on this planet year by year, mostly in low and middle income countries. Most of these deaths could be prevented by early intervention following, of course, early detection of the condition, urging the quest for affordable health monitoring. Can the molecular composition of human blood provide sufficiently comprehensive information to serve as a basis for populational health screening, and can attosecond physics possibly contribute to that? In order to be able to tackle such questions, attosecond technology based on complex vacuum systems has to become simpler and more powerful. And fuse cycle, or actually single cycle light, recently enabled this, owing to its ability to realize the same process that we've just studied in atoms, actually in a wide gap solid, namely optical field-induced electron tunneling. But why is this extreme temporal confinement so essential here? Because no solid matter could otherwise survive the required critical field strength of about 2 volts per angstrom only by confining this extreme field strength to a single oscillation cycle can irreversible breakdown be avoided. Tunneling then occurs within a fraction of the central field cycle in a cosine-shaped waveform. This means actually, again, less than 1 femtosecond for visible or near-infrared light. Sub-femtosecond carrier injection replaces sub-femtosecond XUV light and thereby obviates the need for vacuum systems for a class of applications extraordinarily important for advancing electronics, namely the attosecond control and probing of valence and conduction band carrier dynamics. In a primary step, sub-femtosecond carrier injection is used for optical field sampling. By implementing it in a small volume, where the test field can separate the injected electrons and holes towards 2 electrodes and drive actually a current in an external circuit connecting these 2 electrodes. And here you see this current as a function of delay with respect to the red infrared test field, which is obviously measured with a good fidelity as confirmed by attosecond streaking. Now, this ability to precisely measure the oscillating field of light offers a new probe for attosecond phenomena in the form of the electric field of light, all the way from the infrared, meanwhile, to the ultraviolet. It can actually probe the arguably most fundamental consequence of any light-matter interaction, the displacement of electronic charge density, briefly polarization. It is embedded, it is inscribed in the electric field of the transmitted wave. Referencing this transmitted field to the input field actually allows us to unambiguously retrieve, at least for a thin medium, the induced polarization. Together with its driving field, it actually directly yields, by means of the simple formula, the rate of energy exchange between the field and the electronic system. If we now integrate this rate from a certain time before the electric field is coming in to a certain time point, then we get basically the transferred energy, and that's what I'm showing you here for an insulator and a semiconductor subjected to strong fields. For the highest field strength, the energy transfer appears to be completely irreversible. So basically the transferred energy just stays there after the laser pulse is over. But for reduced field strength, what we see is that actually the field can completely reverse this energy transfer. This is the yellow curve, at least for the 6-photon band gap. And this is a very important regime because such a reversible process is really ideal for dissipation-free ultra-fast signal processing. This regime is completely missing in the 2-photon band gap medium, where reactive and dissipative nonlinearities always appear in combination. These studies actually showcase how real-time access to the light electron energy transfer explores optimum conditions for ultra-fast optoelectronic signal manipulation. We have now seen how light field sampling and the oscillating light as a probe may help advance electronics. In the remaining, yes, few minutes, I would like to address how the same technical capability provides access to minuscule changes in the molecular composition of human blood plasma, and which is a sensitive indicator of health disease transitions. To sense these transitions, we propose, instead of searching for individual biomarkers, actually accessing the global molecular landscape via field-resolved spectroscopy. To this end, we expose human blood plasma, I should say, to a single cycle infrared laser pulse, which coherently excites molecular vibrations within its spectral band. The vibrating molecules in turn radiate coherent infrared waves in the wake of the excitation. The resultant signal, which you see here, is characteristic of the molecular composition of the sample. We capture this electric field molecular fingerprint with highly sensitive attosecond metrology. This fingerprint signal is expected to change whenever emerging abnormalities change the sample's molecular composition, which we recently verified for several chronic conditions such as cancer, cardiovascular, and metabolic disorders. As a prominent example, we compared 470 samples of lung cancer patients with the same number of samples of reference individuals free from cancer, briefly controls, with the two cohorts being carefully matched regarding the distribution of the subject's age and other parameters. These are the electric field molecular fingerprints of all those samples. Clear differences come to light between the two cohorts some 1,000 femtoseconds after the excitation peak, where molecular emission starts dominating over the excitation. We can now quantitatively analyze these differences in terms of the gaps between the adjacent zero crossings of the oscillatory signal, briefly half-cycle gaps. Here we show the mean and the standard deviation of the half-cycle gap, what I would call spectroscopic markers, more than 300 evaluated from the fingerprints of stage 1 to stage 4 lung cancer, from the fingerprints of the controls, and most importantly, the differences between the two cohorts. These cancer-induced signals, cancer-induced changes in the half-cycle gaps range from tens of attoseconds to a couple of femtoseconds. Here we plotted these lung cancer-induced changes in half-cycle gaps for different stages in comparison with the spread of controls. The efficiency with which a well-trained algorithm is capable of distinguishing cases from controls critically depends on this comparison. The classification efficiency can be improved either by increasing the disease-induced signal or by reducing the spread of controls. The cancer-induced signal increases for progressing stages, and so does the classification efficiency, the so-called area under the curve. These AUC values are promising for non-metastasized lung cancer. However, they could be even further improved by reducing the spread of controls, even at the current stage of development of infrared fingerprinting. And that's exactly what our computer modeling predicts for referencing each individual cancer fingerprint to a set of controls collected from the same individual before contracting the disease. The spread of these controls is much reduced, thanks to a strongly reduced within-person variability of the infrared fingerprints over time as compared to their spread in a healthy control group. We pursue proving the predicted performance in a longitudinal follow-up study in Hungary. The predicted above 90% detection efficiencies constitute unprecedented values for stage 1 to stage 4 lung cancer. The price to be paid for this early detection and thereby protection against being diagnosed with the deadly stage 4 will be a yearly blood test. The study in Hungary may reveal that infrared fingerprinting is able to screen other severe chronic conditions at an early stage, and consequently it will become affordable for, if it will become affordable for screening whole populations, may save millions of lives year by year. I take the Academy's decision as a mandate for the pursuit of this very goal with utmost determination. And as a mandate for exploiting our increased visibility for the benefit of the children in Ukraine, who are already dreaming of joining in, like Vladislav, from Lyceum number 10 in Marhanets, near the front line. Just as all other children anywhere else, they deserve a chance to realize their dreams. And we badly need all of them. We badly need all of them to carry on once our own time comes to an end. Thank you.